my first question. Did you know that the energy consumption of computing is projected to reach world's energy supply capacity by 2040? So that's in just 15 years. And this is mainly driven by the exponential increase in the training and use of large data-hungry AI models. And these AI models are being trained by using data centers, which consume hundreds of terawatt-hours of energy per year. And this is already more than 4% of the US electricity demand. And we all know that AI is being used and pursued for a wide range of exciting applications that you are excited about, that I'm excited about. But what I care about most is the very fast increasing energy demand and CO2 emissions of AI. And this is not sustainable. The goal in the field is to improve the energy efficiency of computing by more than 1 million-fold. And this is a very ambitious target. We need revolutionary advances in both software, algorithms, and also in hardware technologies. In my laboratory, my research group and I are working to do our share to advance and enable energy-efficient hardware. A key reason for the large energy consumption of our current computers is the separation of the processor and the memory. And the shuttling of data between these two separate units is very energy expensive. Using our current computers, training of large AI models like GPT-4 is costing tremendous amounts of energy, estimated to be 55 gigawatt hours to train. And even worse, to use it for queries each day is costing 1 gigawatt hour. And this is equivalent to 33,000 US households' energy consumption each day. And as I mentioned a minute ago, these AI models are being trained using data centers, which are costing hundreds of terawatt hours each year. So no wonder why big tech companies like Google, Microsoft, Amazon have been racing with each other in the last year to buy and invest in nuclear energy to power their data centers and using clean electricity. On the other hand, our brains, your brains, are the most efficient computers on things that we humans can learn and do. And this is in large part due to the synapses that connect our neurons, and both the storage and processing of data takes place at this very location, unified in one location, encoded as the synaptic strength. And given that your brains are only 20-watt machines, I have given only 3 megawatt hours of energy to power the brains of my 2 sons, who add up together to 18 years. And when they each become 100 years old, this will have cost only 17 megawatt hours for each of them. So clearly, many orders of magnitude lower energy that we consume to process and learn and function compared to the training and use energy demands of large AI models. Inspired from the neural networks in our brains, hardware, physical neural networks for AI also combine processing and storage memory in one unit, and therefore can reduce the energy consumption of computing substantially. And these hardware neural networks emulate the connectivity of neurons and some functionality of the synapses at the cross points of the array that you see. And it's at those cross points that we shall do the processing and storage, and we can call these devices as synaptic devices. And the conductance at the synaptic device then represents node weights in the physical neural network. So we should be able to obtain many conductance states, hundreds, thousands of conductance states, not just zeros and ones as in our current computers. And the key is to be able to program these conductance states with very low energy and reliably. In the brain, tuning these synaptic strengths, which is literally the electrical conductance across the synapse, is what's involved in many learning processes at a high level. And transmission of small ions under electric potential difference across the synaptic connection is a key process that enables conductance modulation at the biological synapse. And the biological process doing this with transmission of small ions across the synapse in synaptic processing costs only femtojoule, order of femtojoule of energy per synaptic process. That is 10 to the minus 15 joule, and that's incredibly low. And this is taking place in liquid medium, using organic, squishy material. And the question for us is, can we leverage and emulate this super energy efficient process, ionic, super energy efficient process, but by using inorganic materials that we can then use and fabricate energy efficient devices with? And indeed we can. This is why I'm standing here to share some of this work with you from our lab. And we're designing, fabricating, and using artificial ionic synapses where the energy consumption for programming can become even lower than the biological synapse. And these are nothing but, in fact, miniaturized batteries, battery-like devices. And to do the synaptic tuning, we are using the smallest ion, proton, and we run then very low energy, very low capacity, and extremely fast proton batteries. You can view it that way. And in essence, then, by applying programming voltage, we take protons from where they are stored, from the reservoir, and bring them into the synaptic layer that's referred to as the channel layer in this device structure. And every proton that we bring brings together with it an electron, and these electrons become extra electronic charge carriers and increase the electronic conductivity of that synaptic material. And these could be simple binary oxides that are semiconducting, like tungsten oxide, for example. And this process is non-volatile, and if you reverse the programming voltage sign, you can reverse the conductances that you have programmed, and you can do this reversibly, repeatably, many, many times. And the process is analog. It's giving you a continuum of many conductance states, just like in the brain, and not only zeros and ones as in our current computers. And we have leveraged this ionic mechanism in simple materials that we could make nanometer scale devices with. And we have shown that we can obtain conductance modulation very fast, on the order of nanosecond timescales, and with extremely low energy, order of attojoules per programmed state, and that is 10 to the minus 18 joules. So these two together are giving us 6 orders of magnitude faster and 3 orders of magnitude lower energy than the biological synapses in our brains. And this is pretty much the behavior that's needed for analog hardware deep neural networks in the near term. So that is, get me extremely fast conductance modulation with very low energy. And when integrated into next generation AI chips being pursued by chip manufacturers like IBM, Intel, TSMC, these can lead to order of 500-fold improvement in the energy efficiency compared to the current state-of-the-art GPUs. But the brain is more fun than that. There are different types of learning rules that show nonlinear dynamics in time. And these are just a few examples shown on the slide, which illustrate how the conductance change depends nonlinearly on the timing of voltage spikes that arrive at the synapse and taking place at different regions of our brains. This behavior is called spike timing dependent plasticity. And our ionic devices have inherent ability to capture such nonlinear dynamic learning rules, and therefore they can enable even lower energy networks called spiking neural networks for AI hardware. But beyond its energy efficiency, and even more interesting, I think, being able to work with voltage spike trains, so a sequence of action potentials, can allow these devices to enable, in the long term, reliable neuroprosthetics, which can help to replace or improve impaired nervous system functions, for example, by stimulating the visual cortex or by helping to treat certain neurological diseases. And lastly, but also even more excitingly in my opinion, we are targeting longer-term, more biorealistic and more capable AI hardware with our Ionic devices. And there are ever exciting developments in neuroscience which advance our understanding of how we learn. And the prime example to this is the learning rule that describes how baby songbirds learn to sing. And this learning rule has been deduced by experimental neuroscience studies of Michael Fee and his colleagues at MIT. And it's argued that this learning rule has similarities to how humans learn to speak. And we can emulate this essential learning rule not only by using our Ionic devices as the synapses that control the vocal cords, but also as an Ionic control circuit around the synapse. And being able to emulate this biophysical learning rule is a building block for more advanced, more bioplausible, and more capable AI hardware. And it can enable, for example, robots that can continuously learn from the environment and adapt to new situations without having to train them repeatedly, separately, and extensively. And again, being able to do this with very low energy and with a very small footprint, with a very simple footprint, makes it very promising for improving the capabilities of AI. So in summary, hardware physical neural networks can significantly reduce the energy consumption of AI by combining memory and processing in one unit, like in our synapses. And when integrated into next-generation AI chips, they have the potential to improve the energy efficiency by 500-fold at the network level compared to state-of-the-art GPUs. And I have told you that our Ionic devices present with extreme energy efficiency, and at each synaptic process, this actually presents up to 3,000-fold improvement in the energy efficiency compared to GPUs. And these effects can compound to give higher energy gains along the way. And ultimately, these Ionic devices are emulating the Ionic processes that are taking place in our synapses, in our brains. So they have the potential to enable more able, more capable, and lower energy AI hardware. We believe these advances will be critical for the progress of AI in the next decade. Thank you.